Hello and welcome back to Counting Rocks, an Introduction to Combinatorics at CSU. Today we're going to be introducing SAGE, a computer algebra program that's open source and coded by mathematicians for mathematicians, and is a very good tool for doing combinatorics. So I'm going to introduce a bit of basic SAGE syntax so we can use it throughout the course. This is a website, Sage Math Cell. You can go to sagecell.sagemath.org and you can actually just type some code and press evaluate and it will give you the output. So a very simple Sage cell. You can also download Sage onto your computer from sagemath.org and you'll get the full version with lots of coding tools. So here's shown a very simple example of something we can type into Sage and press evaluate. 1 plus 2 plus 3 plus 4 plus 5, and we press evaluate and we get 15. So this is basically looking at Gauss's formula, but just written out from 1 to 5. But we can make this a little more streamlined, especially for, say, adding all the numbers from 1 up to 100. Let's first look what happens when we type range of a number. Range of 11 gives you a list of all the numbers from 0 up to 1 less than 11, so the list from 0 up to 10. I wrapped it in list because that makes it output it as a list, otherwise it'll just say range of 11. But it means the numbers from 0 to 10, and so range of 11 is always a length 11 list starting at 0. So first of all, using the range feature is a good way of looping over numbers. You can also start at 1 if you want, using the following syntax. I added 1 comma 11, and what that means is now it's saying start at 1 and go up to 1 less than the endpoint of the range. So now range of 1 comma 11 would go from 1 to 10, and range of 3 comma 11 would go from 3 to 10. So that's how you can make a list of numbers. Once you have a list, you can do a lot of things to that list. One thing you can do is add up all the numbers in it, using the sum command. So for instance, if instead of listing the range from 1 to 11, we sum the range from 1 to 11, that's adding up all the numbers from 1 to 10. And so that's 55. And using Gauss's formula, we can check that. It should be 10 times 11 divided by 2, and that is indeed 55. So this is showing how we can add things together in a very efficient way using a very simple command, range. You can also use loops over the range command. Here's how we would code it a little bit instead of using the sum command on a list. You would start by typing for I in range of 1 to 11. That means I is a variable that's going to go from 1 to 11 and go through this loop until we're done. We might want to also first set a total to be 0, so we're defining the variable total to be 0. A single equals sign means define total to be this number. And now we're going to add to it each time we have I in range 1 to 11. So we write total equals total plus I. By the way, this colon means that anything below it, we have to put a tab to make it the spacing right in Python. So you use a tab command to make it lined up, so it's saying as long as we're tabbed, we're still in the for loop. And when I untab, that means that what we started with the colon is ended and the for loop is no longer being read. So what this is saying is total starts at 0, and for I in range from 1 to 11, we add I to the total at each step. So we start at 0, and then we add 1, and then we add 2, and then we add 3, and then we add 4, and so on. So far, this is just changing total. Finally, we have to print out total. So the last line of our code should be total after our for loop is all done. So we untab and we write total, and let's press evaluate. And we get 55. So this is doing the same thing as sum of range of 1 to 11, but it's written in a for loop so that now we can actually modify it. If we want to add the even numbers from 2 up to 20, then actually we can just double the I that we're adding at each step. So we can make total equals total plus 2 times I, and that should double this output. Okay, 110. We could have figured that out just by doubling 55. But what if we wanted to add up the squares of the numbers from 1 to 10? Well, then actually we wanted to add I squared at each step. So you can write I to the 2 with a little caret symbol, and that gives you 385. So you can experiment and find different patterns using Sage by adding two things together very quickly. There's also products, so you can also multiply by I squared at each step instead of adding at each step. There's the prod command instead of sum for taking the product of a list. And there's also some shortcut commands. So for instance, factorial and binomial coefficients are things we're going to use a lot. So let's go through some of the combinatorial things now that are already built into Sage. Here's factorial of 5. If you press evaluate on this, it's just going to take 5 factorial and give you 120. So factorials are built in. You can also write binomial of 6, 3, and what does that do? That computes 6 choose 3, because the chooses are also called binomial coefficients, and that returns 20, which is 6 choose 3. So binomial coefficients and factorials are built in. That's going to be very helpful for the stuff that we'll be doing in this class. You can also, in Sage, define variables and work with polynomials, which is going to be a very important tool when we get to generating functions. You can say var of x and expand x squared plus 1 times x minus 3, and that'll expand the polynomial for you. You want to do var of x. X is usually built into the Sage math cell, but in general you want to declare your variables with the var command, and you can list multiple variables in here, all in single tick quotes separated by commas. And then you can just work with them as polynomials. There's a coefficient extender command on any polynomial. When you have a polynomial, you can write dot coefficient of, say, x squared, and that returns the coefficient of x squared in your polynomial. This will be especially useful for the generating functions chapter. Sometimes we'll want to work with matrices. A matrix can be written with a list of lists. Lists are always written in square brackets in Sage, and so I can write square brackets with two square bracket lists inside of it, the first one being the top row of a 2 by 2 matrix, and the second one being the bottom row of a 2 by 2 matrix, and you can always add more rows and make the matrix as big as you like. So here's a 2 by 2 matrix, which it prints out as 5, 6, minus 1, 3. And Sage can do matrix multiplication as well, which will be useful for the graph theory chapter. So for instance, we can square this matrix, and it returns the square of that matrix. Finally, here's how we can draw graphs in Sage, which are a big part of combinatorics. Use the graph command, capital G graph, with, in the input between the parentheses, you write squiggly brackets, like set brackets, and you make a dictionary showing which nodes are connected to which other nodes. So I'm basically declaring that there's a node called 1, and that's connected to vertices 2 and 3, and then a node called 2, and that's connected to vertices 3 and 4, and node 4 is also connected back to 1. Let's see what the output of this is. When we press evaluate, it shows graph on 4 vertices, and Sage does its best to plot the graph in some nice visual way. So there's a lot of more tools for Sage online, and you can look at sagemath.org to find documentation and other code that may be useful throughout the class. These are the basics that we'll need for combinatorics. And that's all for today, and I'll see you next time.